Welcome to the NPTEL online course on fractals and multifractals. So, in the last lectures we have discussed the contraction mapping on a complete matrix where X becomes the contraction mapping on the hyperspace of X with respect to the same contraction factor. Now, let us define the Hutchinson-Barnsley mapping. Define the self map F from the hyperspace of X to the hyperspace of X, where X is a metric space. We can assume that X is a complete metric space. X is a complete metric space, and H of X is the collection of all non-empty compact subsets of X. It is called the hyperspace of X. Now, we are defining the capital F as a function from H of X to H of X by F of A is taking as the union of F1 of A, F2 of A up to Fn of A, where this F1, F2, Fn all are contraction mapping. Each Fk is contraction with the contraction ratio alpha k. Now, we are taking the union of all the mapping. This self mapping F is called as the Hutchinson-Barnsley mapping on H of X. This Fk are contraction on X. By taking the union of all this member, we are defining the mapping F and the H of X. This mapping we can call it the Hutchinson-Barnsley mapping or simply HB mapping. Now, we are going to prove that this HB mapping also contraction. Now, let X comma D be a metric space and H of X be a associated hyperspace of non-empty compact subsets of X with Hausdorff metric HD. If Fk's are contraction mapping on X for all k belongs to Nn, then the HB mapping F is also contraction on H of X. This theorem we can prove by the induction method. So, let us take the n as 2, that means we have two mapping F1 and F2 are contraction on X, two mapping F1 F2 are contraction on X with the contraction ratio alpha 1 and alpha 2. Now, we need to prove that the union of this mapping also contraction in H of X. So, if we want to prove that this mapping is contraction on H of X, we need to take two elements A and B in the H of X, and we need to find the distance between A and B and distance between image of A and B with respect to the mapping F. If the distance between F of A and F of B is less than the alpha times distance between A and B, then we can call it as F is a contraction. So, let us try with this one for n equal to 2. So, the F of A and F of B, we need to find the distance in the Hausdorff distance. Then the Hausdorff distance between this map as per the definition of this map is defined as by taking the union of F1 and F2 I equal to 1 to 2. So, take the Fk of A and Fk of B, union of Fk of B. We know that the each number is a contraction. Also, the previous lectures we have proved that the Hausdorff distance between A union B and Hausdorff distance between A union B and C union D is less than or equal to Hausdorff distance between A and C and find the outstop distance between B and D and take the maximum number, that maximum, the outstop distance between this union is less than or equal to maximum of these two number. So, as per this result, one can obtain the maximum of here F1 of A union F2 of A, outstop distance between F1 of A union F2 of A and F1 of B union F2 of B. So, this is less than or equal to maximum of outstop distance between F1 of A and F1 of B and F1 of A union F2 of B. We'll get this one. So, maximum of this two quantity we can get, this is lesser than this quantity. Whereas, we know that F1, F2 are contraction in H of x. Since the mapping F1 is contraction on x with contraction factor alpha 1, then we know that this function is contraction on the H of x with the same contraction factor. Therefore, the distance, outstop distance between these two element can be written as alpha 1 time distance between A and B. Similarly, F2 also contraction with contraction ratio alpha 2. Therefore, outstop distance between these two element also written as alpha 2 times outstop distance between A and B. Now, here the alpha 1, alpha 2 and we are taking the maximum. If you are taking alphas maximum among these two number alpha 1 and alpha 2, then this quantity is less than or equal to alpha time HD of AB. This can be written as alpha time maximum of HD of AB and HD of AB. So, which is same. So, you can take alphas out, one can get which is less than or equal to alpha time HD of AB. So, F is a contraction on H of x with the same contraction factor alpha. So, we obtained that if F1, if you are taking finite number of contraction and take their union, then union also contraction in H of x. Previously, we saw that if F1, F2 is contraction on x, then F1 is contraction on H of x. Whereas, now we proved that if you are taking the union of these two element, that is also contraction in H of x. Now, we proved this case for n equal to 2. So, one can assume that this theorem, this statement is true for n equal to k, and if you arrived that, one can arrive that for n equal to k plus 1 also this theorem is true by using the similar steps. Then we can conclude that for any given n greater than 1, this theorem is true. Therefore, if we have the finite set of contraction mapping on H of x, simply take their union, it also contraction on H of x. It means that HB mapping is a contraction mapping on a H of x. Okay. For example, we will discuss one example. Let us start with the complete metric space R with the usual metric. Define two contractions. Here two contractions are f1 of x equal to 1 by 2 times x and f2 of x equal to x plus 1 over 3. These two mapping we defined on, or So, f1 is a function from R to R, f2 is a function from R to R. Then what is the contraction factor here? So, one can prove, we already obtained in the previous lectures also, x by 2 minus y by 2 can be written as 1 by 2 times x minus y. Here we are using the usual metric, therefore, we are taking the modulus. So, the contraction factor is 1 by 2, that means distance between f of x and f of y is alpha times, alpha is 1 by 2 time distance between x and y, the contraction factor is 1 by 2. Whereas here if you are finding the f, this is f1, if you are finding the f2 function, f2 of x and f2 of y, one can obtain x by 3 plus 1 by 3 minus y by 3 minus 1 by 3. So, this term will get cancelled, then one can get modulus of x over 3 minus y over 3. So, which is equal to 1 by 3 of x and y. So, distance between f2 of x and f2 of y is less equal to 1 by 3 distance between x and y. Therefore, here alpha you can take as 1 by 3. So, the first mapping is contraction on R with the contraction factor 1 by 2. The second mapping is contraction on R with the contraction mapping 1 by 3. Then, now let us define the union of these two contractions, union of this contraction, that means Hutchinson-Barnsley mapping. So, what is the Hutchinson-Barnsley mapping? Hutchinson mapping is a mapping from the hyperspace of the given complete space. Our complete metric is R. So, f from h of R to h of R we can define as union of f1 and union of f2. Simply I can write, it is written as union of I equal to 1 to fi of A for any A belongs to h of R. So, we define here. Now, let us take two sets, A is 0 to 2 and B equal to 1 to 3. So, basically the 0 comma 2 is our A and our B is 1 comma 3. Maybe we can take it in the larger case. So, maybe we will consider this as, maybe this is here, but I am writing up to this one 0 to 1 and this is 1 to 3. Now, apply the mapping, we need to find the what is f1 of A, we need to find what is f1 of A and we need to find what is f1 of B. So, what is our function f1? f1 is 1 by 2. So, under this mapping x by 2, the image of A is, so it maps to the element. If you are apply this mapping on this set, if you apply f1 on this set, then this map this closed interval 0 comma 2 to 0 to 1. Oh, this is 0 to 2. So, this will map to the 0 to 1, because it is the contraction mapping. The large one is become the just this mapping. When you are applying this mapping on here, it is shrink the whole interval. Similarly, if you are applying f1 on B 1 2 3, if you are applying f1 mapping on B, then one can get 1 by 2 comma 3 by 2. So, it will comes to off. So, here it is 1 by 2 and here it is, maybe I will write 3 by 2. If you are taking the whole interval, it maps here. So, if you are drawing the line here, it is 0 to 1, 0 to 1, 0 to 2, 0 to 3. If you are applying the map f1 on this interval, interval, f1 maps 0, 1 to 0, 2 to this interval, just shrinking here to here, and 0 maps to 0, the 2 maps to 1. When you are applying f2 on 1, 3, this interval, f1 on this interval, it strings 1 to 1 by 2 and 3 to here 3 by 2. Yes, 3 by 2 here. So, the image of 0, 2 and 1, 3 under the mapping f1 is 0, 1 and this mapping is 1 by 2 to 3 by 2. Now, let us find the image of this 2 set with respect to the mapping this one, So, one can get the image of f1 of A is 0, 2, f1 of B is 1 by 2 to 3 by 2. And similarly, if you are finding this one, we have the mapping here, but is the 0 to 3, 0 to 3 we have, we need to find 1, 2, 3, 1, 2, 3. If you are applying the mapping f2 on this interval, if you are applying this interval, then this whole interval, it maps to f2 of A is 1 by 3, 1. So, 1 by 3 is maybe here, and if you are applying 2, 2 will becomes 1. So, this goes to here and 0 goes to here, just stringing in the both side. Whereas, if you are applying the same mapping on 1, 3, this interval, if you are applying f2, then it maps f2 of B is 2 by 3 and 4 by 3. So, 1 by 3, this is 2 by 3 maybe. So, it maps the number 1 to 1 by 3 and 3 to 4 by 3. So, 4 by 3 approximately here. So, it maps here. So, it is shifting both the side. Now, f of A is, this is f1 of A and f1 of B. This is f2 of A and f2 of B. Now, we need to find what is f of A. So, what is f of A? F of A equal to f1 of A union f2 of A. Similarly, f of B is f1 of B union f2 of B. If you are taking the union of these two set, one can get the interval 0, 1 because this is contained in this set, and similarly this set is contained in this one. So, one can get this set for f of A and f of B. Now, this is f of A and f of B. Now, what is the Hausdorff distance between A and B? We need to find the Hausdorff distance between A and B. What is the Hausdorff distance? We have the set 0 to 2 and 1 here, 1 to 3. So, we need to find the Hausdorff distance between this one. So, Hausdorff distance between these two sets A and B, find the difference between these two number and find the difference in these two number and take the maximum. So, that means this lower element to lower element, this number, and upper element to the upper element. So, both are equal to 1. So, Hausdorff distance between A and B, one can get as 1. Similarly, we need to find the Hausdorff distance between f of A and f of B. So, for finding the Hausdorff distance between f of A and f of B, let us find the Hausdorff distance between f1 of A and f1 of B. So, f1 of A is f1 of A is 0 comma 1 and f1 of B is 0.5 to 1.5. That means, if you are taking 0 comma 1 and this is here 0.5, if this is 1.5, then this two number we need to find and take the maximum. This is equal to 1 to 1.5 is 0.5 and 0 to 0.5 also 0.5. Therefore, the Hausdorff distance between f1 of A and f1 of B is 1 by 2, and similarly the Hausdorff metric between these two elements f2 of A and f2 of B. So, here f1 of B is 1 by 2 to 3 by 2 and 2 by 3 to 4 by 3. We can subtract this two number and take the maximum. So, one can get which is equal to 1 by 3. Hausdorff distance between these two is 1 by 3. But we know that while finding the Hausdorff distance between these two number, which is less than or equal to Hausdorff distance between f of A and f of B can be obtained as, this can be, we can write as Hausdorff distance between f1 of A union f2 of A, comma, Hausdorff distance between f1 of B union f2 of B. We can apply the previous theorem, which is less than or equal to maximum of Hausdorff distance between f1 of A, comma, f1 of B and Hausdorff distance between f2 of A and f2 of B. So, if you are applying this one among these two number, the maximum is among these two number 1 by 2 and 1 by 3, the maximum is 1 by 2. Therefore, the Hausdorff distance between f of A and f of B is 1 by 2. So, Hausdorff distance between A and B is 1, Hausdorff distance between f of A and f of B equal to 1 by 2. Therefore, one can conclude that Hausdorff distance between f of A and f of B is less than or equal to 1 by 2 times Hausdorff distance between A and B. So, here this 1 by 2 is act as a contraction ratio of the Hutchinson mapping F, which is defined with respect to the two functions here. So, how we define the Hutchinson map? Hutchinson map f of A from this hyperspace is defined as I equal to 1 to 2 this f I of A. This mapping, if we are taking f1, f2 or two contraction mapping with the different contraction ratio, then f is a union of these two contraction mapping f1 and f2. Then as per the previous theorem, this is a contraction which we proved in this result. Also, what is the contraction factor for this? If we are saying this one as the contraction mapping, we need to say what is the contraction factor. So, for the contraction factor, we can find the maximum among this one. So, here we are obtaining the contraction factor as 1 by 2, since the first mapping f1 as the contraction mapping 1 by 2 and the second mapping f2 as the contraction factor 1 by 3. So, the contraction factor is maximum among this two number. So, from this theorem one can conclude that the Hutchinson mapping F is a contraction on H of x, that we proved with the example. In this example also says that the maximum of these two contraction will give the contraction factor of the given number. Now, you can just summarize our result in these lectures. We define the Hutchinson mapping on H of x, and we proved that the Hutchinson mapping is a contraction mapping on the H of x. In previous lectures, we have proved that if x is a complete metric space, H of x also complete metric space. Now, you can think that if we define the Hutchinson mapping F on the H of x, that means the complete metric space, what will happen? That will be discussed in the next lecture. These are all the some references one can refer. Thank you.